Yeah. Okay, so let us take and also let me write down. All right, suppose there is one mistake, unfortunately. This one, just noticed it. This is a mistake. This will be AX or B. I'll correct it. This will be AX or B. This is a mistake. I can actually correct it right away. If you just well, I'm not getting it just now. Sorry. Uh, okay, yeah, AX or B. I'll have to reopen it with this, unfortunately. It will not refresh on its own. Yeah, I think that problem is corrected. Okay. Yeah, so we have, okay, so suppose we take a function like this. Suppose I write an expression like this. Let us say A plus B, all right. And if I say, uh, if I say, um, times A bar B. Suppose I just write an expression like this. A or B and A bar or B. So of course you can do it algebraically, that is one way of doing it. But what I would just like to show you is that, I mean, this you probably know. So this is A plus B. Let's put it here. Yeah, so this is A plus B, and this is A. So now, as you saw last time, um, this AND operation is the join, is the meet, okay? It's the meet operation in the lattice. So can you find the meet of these two in the lattice? So let us see if you can find the meet of these two in the lattice. So this is, if you look at this is the meet. Of this and this in the lattice. So, you know, this lattice uh, shows you, and if you take the join, for example, if you take the join, if you write All right. Of course, it is quite evident that this one you have A or A bar, so you expect it to be 1. But you can also see it in the lattice. Let me so maybe if I put the join in a different ink. Uh, so so this is the meat. This is the join, and this is the meat of this too. So this way actually you can compute the meat of any two. So you can just, so why don't you just try it out for, I mean, just take two other nodes. You can take any two nodes. I mean, let us just take, so this you can do on your own. Why don't you try on your own? This one and maybe this one. So why don't you work out on your own and tell me the result of this? Yeah? Can you work out and tell me the result of this? What will be the meat of this and this? You can do it in the lattice and tell me. Anyone?
Join is A plus B bar and meet is A B bar.
So join is a plus b bar. So how do you get it? You can, yeah. So join, as you can see, you can, yeah. So if you follow this path, so uh, this gives you the, this path helps you to get the result. Yeah. Yeah. Okay. So you can use the lattice. I mean, these are just meet and join operations in the lattice, and you can also do the same using algebraic simplification. So uh, yeah. So the important aspect really is the computational one. I mean, uh, so from this you can see that what you want to do, these are all lattice operations. So what is the challenge? The challenge is handling the computational complexity. All right. So we'll be looking at some standard algorithms which have evolved to uh, to uh, optimize Boolean expressions. So you can, think of these as optimizing. I mean, this by itself, what we have here by itself, these are Boolean expressions. But we would prefer to have simpler forms of these. All right, we'd like to have simpler forms of this. So what you can see is that um, doing that is essentially, you can look at it as either algebraic simplification, or as, performing operations on the lattice. So we will look at some standard techniques. We'll look at First we'll look at, we'll just look at two standard techniques. One is called Carnot maps, and the other is called Quine-McCloskey. Quine-McCloskey method. I hope I've got the spellings right. So we'll be looking at this pretty soon. So let us just carry on with the slides, and yeah. All right. So yeah. So this is a way of interpreting your complement. So x bar of the complement of x is 1 if and only if x is 0. Acceptance of products xy is 1 if and only if x is 1 and y is 1. Acceptance of sum is, u or v is 1 if u is 1 or v is 1. Then we have this mean term expansion that you have already seen. So from these, these are your, your basis for, acceptance. These are your basis for acceptance. So now you can, recursively formulate the acceptance of a mean term. So now this you can see that by this definition. So if you have a mean term, so a mean term the acceptance of a mean term can be determined by the acceptance of the products. That means if you have a mean term something like xy bar, so this will be accepted if and only if x equal to 1 and y equal to 0. Anyway, so that you can very well see. And if this acceptance of a mean term expansion simply means sum of mean terms. So that will of course go by the sum rule. That means if at least any one of the mean terms is true. And in case of mean terms, as you have seen, that these are actually the atoms of a Boolean lattice. So only one of them can be true. You'll never have more than one mean term true. So we are saying that if you have two mean terms, mi and mj, defined on some variables x1 to xk. So these two are not identical. Okay, so if these are not identical, then there must be some variable on which they differ. So let us say that they differ on xp. So if they differ on xp, so so yeah, so xp will occur as a literal. So when you say that it occurs as a literal, so that is, let us say, xpi and xpj. So xpi and xpj, so one of them is x and the other is, sorry, yeah, okay, one of them is xp and the other one is xp bar. So one of them will be xp, the other one will be xp bar. That's what it means. Okay. So one will be the complement of the other. So if mi accepts, then mj doesn't accept, and vice versa. So that is just a formalization. I mean, we are just justifying this, that um, this is what we are just justifying. That is by exactly one mean term. So what you can see is that uh, uh, only this sum, when you have this sum, it can be accepted. Acceptance happens. The acceptance of the sum happens due to the acceptance of exactly one mean term. So only one mean term can be true or accepted. All right. We have already looked at the number of Boolean functions in significant detail. So I'm just going to skip through the slides. But I think these things we have already done in the class. The number of, yeah. So this is the number of atoms that you have. For example, with a two variable function, you saw the atoms, I think, A bar, B bar, A bar, B. So you have seen these atoms. So you have, 2 to the power 2 atoms. And the total number of elements in the Boolean lattice is 2 to the power n. All right. So these things you have already seen. We have also uh, uh, looked at it from the truth table point of view. This we have already done in the class. So you have, when you have a truth table, you have, as we have seen, that n equal to 2 to the power k mean terms. and you have 1, 0, 1, etc. to the power n ways of keeping or choosing these. All right, so either way you have this number. So if you have k variables, you have 2 to the power 2 to the power k Boolean functions. All right, so this we have already seen before. We so Boolean expression manipulation. I mean, you can use the laws of Boolean algebra to manipulate Boolean expressions. So these are some examples of those. There are some examples of those. So let us just look at some functions. So you are already familiar with XOR. So you know that XOR is both commutative and associative. Okay, XOR is both commutative and associative. So you can write the XOR of A, B, and C as just A XOR B XOR C. You can evaluate it as you like. In each case, you will have the same result. This is also interesting. So, AND distributes over XOR. Okay, AND distributes over XOR. So these are easy to establish. You can, yeah. And if A XOR B happens to be equal to C, then either A XOR well, then you have these properties. So if A XOR B is C, so all these properties hold. I think these are fairly intuitive, so you can verify these as well. Yeah, so we'll just take a look at series parallel switching circuits. So we have looked at Boolean gates. We have looked at Boolean gates like XOR, AND, OR, NOT, etc. Many gates. We also have series parallel switching circuits, which you have actually seen before in the very early lectures. You have looked at those CMOS circuits. So the operation of those CMOS circuits can also be expressed through series parallel switching circuits. So so if you have, these are some ways of showing denoting series parallel circuits. So If a gate is normally closed, it's sometimes represented, it's called primed. It's not, I mean, these are some standard nomenclatures for series parallel switching circuits. So these may be used in many, practical examples as well. All right. So series connection is denoted by AND, parallel connection is denoted by OR. So you can have uh, a transmission expression of this form. So you can say that uh, you know the circuit will transmit if either you know x is, if you go by this convention, if you go by this convention, so this means x is open and y is closed, or if z is closed, then if x is closed or y is open. All right. So this is, we can say, a transmission expression. And these can be simplified. So in this case, this transmission expression has been simplified to just this form. So here we have just multiplied, or you can say that you have distributed z, or you can say that this is AND. You have distributed this AND operation over OR, and you have got this expression. And then you have carried out some further simplifications and got this expression. All right. And you can see here, this one is 1, so this is z. That's what you have here. So like that you can simplify. And if you look at this is, so you get this form. So you can do such algebraic simplifications. All right. So this series parallel circuit operation. I mean, you can draw these circuits. Of course, you can draw these circuits. You can uh, say, uh, if I just take this expression, this is slightly simpler. So this simply says that, so x is, um, if I say x is, sorry, so I can, say that if I'm I think if it is normally open, I might be making a mistake. So this it's saying that, so this is So this is just a series parallel circuit, that's all. Uh, so this is a relay circuit. Okay. So this is normally closed. This is X bar. Okay. I mean, this is X bar. So this is say normally closed. This is normally open. So this is normally open, and this is also normally open. So this relay will close if you make Z1 or X1 and Y0. So that is when this relay circuit will close. So what this is simply saying is that you can optimize relay circuits in the same way. So this expression was, denoting X. Uh, oh, here, sorry. Uh, the convention that I have followed, this is X, this is, and then this is in, so maybe I should, yeah, this is, so this relay circuit is equivalent to this relay circuit. That is what we have done. All right. Okay. Uh, yeah, so Shannon decomposition, I mean, we have already worked out Shannon decomposition in significant detail, so I'll just skip through the slides, that's all. This is the dual. These are. So we have in the lab we have looked at this thing. This is just a dual statement. This is just a dual statement. Dual expansion. All right. This is just a dual expansion. So we have seen that we have looked at the principle of duality. So this is the dual expansion using um, using product of sum rather than sum of product. This is a sum of product. So this is POS expansion. Yeah, and we have seen how you can use a multiplexer realization of the Shannon decomposition. All right. So, with this we complete the basic introduction to your Boolean algebra. I think we are nearly to the end of this class. I think I'll just stop today instead of starting a new topic now. We'll just stop here. We'll take up Boolean function optimization in the next class. All right. So, yeah, Pavitra, do you want to say anything? Otherwise,
No, I think it is fine. So we have already declared the syllabus for the class test.
yeah,
So you can, I suggest that you study the assignment problems.
yeah, okay. All right then. Yeah. So we
So
have.
I think, yeah, so we have declared the class test Wednesday. Syllabus, everything is declared. So they should practice the assignment problems. It will help them in their test.
Yeah. So you have been given these assignments. Do practice these assignment problems. Yeah. Okay. Okay. Then we'll stop here now. Yeah.
Yeah.
Okay.